huge.
I was like looking at my email and I just got that.
10 megabyte for a single page. Like, good night. Like, well, it's not your fault. It's Apple.
Got a great deal on green.
All right. I will start. Since I'm a minute late, I'll go a minute over. I'll begin with a scripture here. So this is Proverbs 26, verse 4 and 5. Interesting verses. Do not answer a fool according to his folly, or you will also be like him. In verse 5. Answer a fool as his folly deserves, that he not be wise in his own eyes. It's like, wait, what? Wait a minute. So which are we supposed to do? I don't know. I think if you take a good look at the world right now, these are really relevant verses. Like, there's a lot of people answering fools to their folly all over the place, you know? But anyway, I'll begin with a word of prayer. Heavenly Father, we thank you for this day and this opportunity we have to meet and study your creation. Just pray that you'd be glorified in what we do, and then we'd understand a little bit more about coordinates and bases and things together. In your name I pray, Lord Jesus. Amen. All right, so I think in good conscience before this point I could have said to you, go read my notes. They're pretty much a good faith parallel to what we're doing. At this point, though, chapters 4 and 5 of my notes, there is a sprinkling of abstract vector spaces in there, and you're not responsible for that in this course, right? So I'm keeping it real for the most part in here, in the sense we're studying Rn and, you know, the structure of Rn and matrices, transformations on n-dimensional Euclidean space for the most part. So I just want to warn you, there's a few things in my chapters 4 and 5 which are on abstract vector spaces. When I say look at the chapter, I'm not saying you have to learn that stuff necessarily. Wouldn't hurt you, but I won't test on it. Now, the other thing I would say about chapters 4 and 5 is that you may find as you read the examples in chapter 4 and 5 that you wish you read them before my test 1. Because there's a lot of examples in there which I hope will further clarify the column correspondence principle, the concept of spanning, the concept of linear independence. All right, there's just a complete calculational theory of how to deal with spanning and linear independence in those chapters. All right, but my larger point to you is I really need you to follow what I'm doing in class for this part of the course. All right, so the class will have what my heart is for you in terms of what this course is about here, and the homework that I've written for you guys reflects what I'm about to do, okay? So let's talk about coordinates and bases then. All right, so just a reminder, definition, a basis for Rn is a set of vectors. All right, I'm going to use beta typically for the basis. Beta, so v1, v2, vn. All right, it's a set of vectors which is linearly independent, and the span of beta is equal to Rn. Now, I guess I should probably qualify here some theory that we haven't really done in here, but I'd like you to know. So here's some theorems that I should probably mention to you. So here's some theory that we probably haven't really done, but it would be worth knowing. Any set of k greater than n vectors is linearly dependent. In Rn. So if I had, for example, if I had 4 vectors in R3, the set of 4 vectors in R3, it has to be linearly dependent. You simply cannot have 4 linearly independent vectors in R3. There's just not enough room for it. In R2, we can't have 3 linearly independent vectors. All right? Now remember, linear independence is something we talk about for a set of objects, right? So I could have 3 linearly independent vectors which pairwise, I can have 3 vectors in R2 which pairwise are linearly independent, all right? I just can't have them as a set of 3 to be linearly independent. And then the other thing is, any set of n linearly independent vectors in Rn is necessarily a spanning set. In other words, what I'm trying to say is if you have n linearly independent vectors in Rn, you can build any other vector as a linear combination of those. All right? So I don't think I've quite said those things in here before, but I should. Those are actually kind of like guiding principles for what we're doing going forward, okay? So a basis is a linearly independent spanning set. Now remember, what does that mean? What is one of the things about linear independence that we have? Well, let me remind you this. If we have C1v1 plus C2v2 plus plus CnVn, right? And it's equal to, let's say, B1v1 plus B2v2 plus plus BnVn. Do you guys remember what we proved the other day? It's been a couple weeks since we did this, but one of the things we showed was that that implied what? What did it tell us? It told us that Ci is equal to Bi for all I, right? So with respect to a basis, we can equate coefficients, right? So we can equate coefficients. Can equate coefficients for a basis. All right, and because you can equate coefficients, the definition I'm about to make is meaningful. All right, there's no ambiguity in the definition I'm about to make, which is this. So if we had x was equal to this right here, did you guys get that? If x is equal to that, then we can define the coordinate of x with respect to beta to be C1, C2, Cn. So this is the coordinates of x with respect the beta basis. Right. Now let me do something a little bit more here, just for the sake of notation. Let me just start over here, actually. So that's fine. It's fine. But okay. So if let's say if beta bar is v bar 1, v bar 2, v bar n, right, is basis for Rn, and x is equal to, say, x bar 1, v bar 1, plus x bar 2, v bar 2, plus plus x bar n, v bar n, then the coordinates of x with respect to the beta bar basis is equal to x bar 1, x bar 2, x bar n, right? So I'm just doing the definition again, but with respect to the bar basis, all right? So like an immediate question you guys should ask, right, is what about x is equal to x1 e1 plus x2, well, remember we have this? If we have x1, x2, xn, then that's what? That is equal to x1 e1 plus x2 e2, right? Plus xn en. What is it? Oh, I need to collect homework. Yes, please, turn your homework. I don't want your current homework to distract you from my lecture. That would be bad. What am I thinking? I forgot the basic nature of students. Thank you, thank you. I guess I'll come behind you. Thank you. I should have made an announcement to the CFA office or whatever. I guess I won't collect. You're not in this class, right?
No, I'm
Okay.
CFA.
C for CFA, okay, good. Just checking. I usually know my students by now, but every so often. So my point to you is, what's the coordinate vector of x with respect to the standard basis? So here, if we just let's say gamma is the standard basis, which is what? E1, E2, En, right? Our usual meaning for E sub 1, E sub 2, which is what? It's just like, you guys know, E1 is 1 with zeros all the way down, right? En is zeros with 1 in the last spot, right? So here's the standard basis. We called that before, but we meant it. It is indeed a basis in this sense we just defined, standard basis. So check this out. What's the coordinate vector of x with respect to the standard basis? So the question is, what are the coefficients that you need to build the vector? That's what defines the coordinate vector. So the coefficients we need are x1, x2, all the way to xn. But what is that? That's just x. That is literally just x. So every vector is its own coordinate vector with respect to the standard basis. But with respect to a non-standard basis, well, it's a more interesting question. All right, so let's look at an example with some numbers in it to get a little bit more understanding here. I'll start out with a really easy example. Let's look at the basis, which is E3, E2, E1. One of the things I should have mentioned and really emphasized is it's not just a set of vectors. It is, I'm missing an n here, and I'm missing a caret, and the word ordered. That's important. See, because the ordering matters, because you're picking off the coefficients of the sum to put here. They have to be in order. So if my basis is E3, E2, E1, right, namely 0, 0, 1, 0, 1, 0, and 1, 0, 0, right? That's what those are in R3. If I have the vector v equals to a, b, c, right? That is what? That is c times E3 plus b times E2 plus a times E1. So therefore, the coordinate vector with respect to beta of this vector v is what? So c is the coefficient of the first thing in the basis, b is here, and a is down here. We can just figure this out by just looking at it. And if we understand the definition. Now let's look at one that's not so easy. Example 2. Suppose we have beta equal to, let us say, 1, 2, and, well, let's say 2, 1. 1, 2, 2, 1. That's a basis for R2, right? And let's think of this, let's call this thing V1, V bar 1, and let's call this thing V bar 2. All right? I'd like to derive the formulas for the x bar 1 coordinate and the x bar 2 coordinate. All right, so if we have x comma y, and we're writing it as x bar 1 v bar 1 plus x bar 2 v bar 2, can you guys tell me how to figure out what's the formulas for x bar 1 and x bar 2 in terms of x and y? How would we do that? Well, let's look at it. So what we're looking at is x bar 1 times the 1, 2 vector, right, plus x bar 2 times the 2, 1 vector. Let me rephrase this again. So really what we're up against is the matrix 1, 2, 2, 1 times x bar 1, x bar 2 is equal to xy. Do you guys follow me what I did there? So I rewrote the matrix, the vector equation as a matrix equation. And I made the left-hand side the right-hand side, I suppose. Yeah? How do you solve that equation? How would you suggest I solve this? You're like Kramer's rule. Like, no, stop that. I mean, you could if you wanted to, but how about just multiplication by the inverse, right? So multiply by the inverse matrix, and we get x bar 1, x bar 2 is equal to the inverse of that matrix, which is what? 1 over 1 minus 4. Flip the diagonals. That's kind of boring. Minus is on the off diagonal. xy, which apparently gives me minus 1/3. And then I've got an x minus 2y and a minus 2x plus y. All right? Putting it all together, we just found the formulas. X bar 1 is equal to, we could say minus 1/3 times x minus 2y. And x bar 2 is equal to, I'll put the minus through there. So 2x minus y, let's say. And there you go. That's the change of coordinates. Those are the change of coordinate formulas. Now, we'd kind of like to have a nice, concise theorem for doing this in the future, right? So let's derive a nice formula for all this. Let's put it into simple terms. So let's look at a certain calculation. So consider if we have x is equal to x bar 1 v bar 1 plus x bar 2 v bar 2 plus dot 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 plus x bar n v bar n, right? Then we can rewrite that simply as the matrix v bar 1 v bar 2 dot 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 v bar n times the column vector x bar 1 x bar 2 x bar n. Write that. And let me make a definition. So if I'm still using the notation like beta bar for this basis. If you guys let me continue using that notation. All right. So this right here we will call the beta bar basis matrix. So this is a new notation. If we put square brackets around a set of n vectors in Rn, that means we're making a matrix formed by just gluing the vectors in that order. So it's not just a set, it has to be an ordered set because like it matters which order. The first one goes in the first column, the second one goes in the second column, and so forth. Is that right? If I wasn't ordering things, we couldn't distinguish example 1 from the standard basis. Do you see that? Like example 1 is the standard basis, just in a different order. That is a different coordinate. That's a different basis. And we get a different coordinate, right? This is not equal to v. V would be its own. If V is equal, if the coordinate vector V is equal to V itself, we're talking about the standard basis. Only for the standard basis do we have a vector as its own coordinate vector. Otherwise, it's usually something different. All right, so anyway, in this very much better, that doesn't sound like very good grammar, in the basis matrix here, we had a name for this. This was the coordinate vector of x with respect to the beta bar basis. Let me rewrite that again. We have x is equal to the beta bar basis times the coordinate vector of x with respect to the beta bar. If I want to find a formula for the coordinate of x with respect to the beta bar basis, what should I do? How do you solve? In other words, I want you guys, how would you solve for this? What do you do? Yeah.
Multiply both sides by the beta bar inverse.
Now, why do you know that? Why does beta bar inverse matrix exist? I agree with you, but why does it exist?
Because for it to be linearly independent, it has to have like the same number of rows as columns.
For it to be linearly independent, it has to have the same number as rows as columns. Interesting. Yes, I mean, I think what you're saying is the reducer echelon form of the beta matrix has to be the identity matrix. Like you're thinking back to that list of equivalent statements we had. If we have linearly independent vectors, if we have a set of n linearly independent vectors, that means that the reducer echelon form of the matrix, by gluing those vectors together, has to be the identity matrix, which also meant in turn that there has to exist an inverse, which also meant we had a list of like 7 other things, right? So it's exactly that, though. That's right. So yes, it has to exist because we're assuming linear independence of the vectors forming the basis in a nutshell. And so there you go. That is how we find the coordinate vector of x with respect to a possibly non-standard basis. Here's the thing. For the standard basis, see what happens for the standard basis? Something silly happens. Right? You've got, if I still use gamma, gamma, by the way, is not always the notation for the standard basis, but since I was using that earlier today, like what's this? What's this matrix for the standard basis? It's what? It's the identity, right? So this formula just becomes x equals x, basically. X bar, coordinate vector with respect to gamma equals x in the case of the standard basis. All right. How could we make this easier? Can we make it easier? I would say for problems in the wild, let's say, no, I don't think you can make it easier. Like, it is what it is. To find coordinates with respect to a non-standard basis, we just have to deal with the problem of inverting the basis matrix. Like, that's the difficulty. That is what it is. However, certain matrices are easier to invert than others, aren't they? Right? So let's look at another example here. All right. So what example am I on? 3. All right. Example 3. So let's consider 2xy equals to 1. I want to find a change of coordinates which reveals the true nature of this equation. All right? So I can't really quite derive all that for you, so I'm just going to, this is sort of a magical step right here, but I believe we can consider the basis 1 over the square root of 2, 1, 1, 1 over the square root of 2, 1 minus 1. Oh, I guess there's another thing I was going to tell you at the start of class. I just forgot. How can you judge whether or not, all right, so let's start at the beginning. How do you judge whether one vector forms a linearly independent set in and of itself? This is very dumb. There's only one, if you have a vector, There's only one way it cannot be linearly independent, which is if it's the 0 vector. All right, so 0 vector is not linear. The 0 vector on its lonesome is a linearly dependent set, by definition. If you have 2 vectors, when are they linearly dependent? If you have 2 vectors, you can prove that 2 vectors are linearly dependent if and only if one of them is a multiple of the other. So for 2 vectors, if they're collinear, if one is a multiple of another, they're linearly dependent. Otherwise, it's linearly independent. Are these linearly independent? Absolutely. It's clear that one is not a multiple of the other, right? Okay, so for 3 vectors, it gets more complicated to say exactly what it means for 3 vectors to, not be linearly dependent. I mean, we had the characterization they're not coplanar, right? We could do that. But anyway, let me focus back here. So let us, again, for the sake of notational consistency, I'll call this v bar 1, v bar 2, right? So I want to find the formulas. I want to find the formulas for x bar 1 and x bar 2 like I did in the other example, okay? So how do we do that? Our basis matrix here is what? I got a 1 over root 2 everywhere, so I'm going to pull that out front. And we'd have 1, 1, 1, minus 1. So what's the inverse of this matrix? So we can do what? I guess, oh man, I'm sorry guys. I mean, this is not wrong, but to do the silly inverse formula, it kind of helps me to see this. Otherwise, I'm thinking too much. I don't want to think too much. You guys don't want me to think, right? Actually, if I was going to be really lazy, I'd just point out to you that this is a rotation matrix. It's just like, oh, wait a minute. No, it's not. Dang. Sorry, let me go on. Let me not. I've got some kind of mental block at the moment here about that. So anyway, we can invert this. What's the determinant?
1 over -1.
Yeah. Okay. 1 over -1. Very good. And then we flip the diagonals for the defloppity. And we put minuses on the off diagonals. And we clean this thing up. So it's 1 over root 2 times what? 1, 1, 1, minus 1? What? Oh, that's weird. This matrix is its own inverse? Dang. My mind is being blown. Oh, the determinant's -1. Okay, so this is not a rotation, it's a reflection. I just wanted it to be a rotation. Let me get over it. All right, let's go on. So that is what it is. All right, so then using our general theorem, we have x bar, let's say x bar y bar is equal to 1 over the square root of 2, 1, 1, 1 minus 1, xy, what do we get? I get 1 over root 2, x plus y, x minus y, right? And so that tells me that x bar is equal to 1 over root 2, x plus y, and y bar is equal to 1 over root 2, x minus y, which is wonderful, but it doesn't help me with the original problem, does it? Because what do I need to do in order to convert my given equation into the barred coordinate system? What do I need to do? if I want to convert this to a formula in the barred coordinates, I need what? I need formulas that tell me what x and y are in terms of x bar and y bar, right? I have to have the other way around. So that's easy enough to do. We just multiply this by the inverse, which weirdly enough, I'm sorry, this is really weirding me out, but the matrix is its own inverse. It's the same stupid thing. Man, that's weird. Sorry, guys, I'll get over it eventually. But my point is that the same formulas hold the other way around. That is so weird. If I wanted this to happen, it wouldn't have happened.
Shouldn't it be
What did I do?
root 2, not 1 over root 2? You do the inverse? I can never hear this back.
But the thing is that this matrix is its own inverse.
Right.
So basically, like, let me just put it at another level of notation. We have the equation v beta bar is equal to beta bar inverse times v. So I'm multiplying by beta bar times v. The point is that this is this is, look, the inverse of is the same as I seem to, oh man, I'm sorry guys, I'm starting putting bars everywhere. Fine. Just trying to be consistent. There. All right. Now that we have that, what happens to our original equation? What happens here? We got what? We've got 2, 1 over the square root of 2. What's x? X is x bar plus y bar. And then 1 over root 2, x bar minus y bar, right? Equal to 1. So that just gives us what? X bar squared minus y bar squared equals to 1. What's going on here is something kind of neat. If you were to, say, graph what's going on, I think it's interesting. So of course we know x and y are like that, right? How about the x bar? What are the equations of the x bar and the y bar axes? Like, how do you find the equation of the x bar axis? X bar axis, let's think about this. The x bar axis is where what? Where's the y axis? It's where what? X equals to 0. Likewise, the x bar axis is where y bar is equal to 0. Where's y bar equal to 0? Y equals to x, right? And if you look at it, I believe you can see that well, I mean, anyway, so the point is it's 1, 1. So the x bar axis goes like this. That's the x bar axis along y equals x. It's not an accident. That points in the direction of the 1, 1 vector, okay? Yeah? Now the 1 minus 1 vector is going to be like this down here. All right? The formulas would have been less weird if I had instead have chosen like minus 1, 1 instead of 1 minus 1. I would have been less weirded out by that. The reason I'm weirded out by this is, like, we're going from a right-handed coordinate system in the sense that we take the E1 and we counterclockwise rotate into Y, into E2. So like the standard coordinate system is right-handed in the sense that you rotate from the first basis to the second basis in a counterclockwise fashion. My new basis is clockwise oriented. See, I go in the first basis element like this, and I have to rotate clockwise into the second basis element like that. See, guys, this right here is v bar 1. This right here is v bar 2. Okay? And what is this equation? Do you guys know what this is? It's a what? It's a hyperbola, isn't it? That's a hyperbola which opens which way? If I look at x bar equals to 0, it has no solution, right? Because you get negative number equals to a positive. So it is a hyperbola which opens up like that. Maybe I should use a different color, but let me use a different color. All right, so this is the equation 2xy is equal to 1. You've perhaps heard it said before that the reciprocal function is a hyperbola. All right? We are now discovering the mathematical technology that you need to make that prove it, to explain why, to see how that actually is accomplished. Did you guys see? So here, this formula, I mean, of course, this is simple enough formula. You know what to do, right? You know how to graph a reciprocal function, right? So my example isn't that awesome, but it is very neat, I think, to see its true character revealed by this change of coordinates. So this is the kind of thing we're after going forward. We want to learn not just how to change coordinates. I mean, that's the first thing we got to learn is how to change coordinates. That's actually pretty simple. I've showed you the formula you need to do that. It's in a box over there. That's it. So yeah, we want to learn how to change coordinates, but why do we want to do it? We want to do it so that we can expose hidden features of equations and then soon transformations, right? We're about to start talking about linear transformations. But I thought it would be helpful to first talk about the basis concept, because I think the concept of a linear transformation is actually pretty simple. That's not too bad. This is the thing you guys have more trouble with, so I thought we should lead with this. That way there's a little bit more, there's a little bit more daylight between this and the time I test you on it, right? So anyway, there's that. Another thing I should talk about today is nice bases. So what I mean by a nice basis. Oh, lest I forget. There you go. You can add a day for me. That would be awesome. All right, so example 4. Let's suppose we've got basis beta, and I guess I'll still do bar again here. Oh, fine, I'll just do beta. So U1, U2, U3, all right, where U1 is 1 over the square root of 3, 1, 1, 1. U2 is 1 over the square root of 2, 1 minus 1, 0. And U3 is 1 over the square root of 6, 1, 1 minus 2. All right. So let's see here, and we'll think about the equation for the sake of for fun. How about 9x squared plus 9y squared plus 29z squared. Let's see here. Plus I don't know, 14xy minus 26xz minus 26 yz equals to 1. So then my question is, what's that? All right. So let us work out the change of coordinates formulas for this one. Check it out, though. It's not, oh, OK. It's not too bad, believe it or not. Because in this one, if I want to calculate the coordinates of x, y, z with respect to the beta basis, I can do x, y, z. My bad. What I can do is x, y, z dot u1, x, y, z dot u2, x, y, z dot u3. Now, why can I do that? So here's the thing: is this basis is what? What kind of vectors are these? I probably owe you guys a short derivation. So like if you have, let us say v equals to x bar 1 u1 plus x bar 2 u2 plus x bar 3 u3, if I take v, I guess I'm calling this x, so let me stick with that. If I have x dot u1, what's that give me? So what is u bar? What is u1 dot u1? Can you guys see it? It's 1 plus 1 plus 1 is 3, divided by the square root of 3 squared, which is it's 3 over 3, which is 1. So this is 1. This is 0. This is 0. So to calculate the x bar 1, I simply take the dot product with u1. Likewise, I simply take the dot product with u2. I take the dot product with u3. I can do that because this is an orthonormal basis. And so we can straight up write down the formulas. We got like 1 over the square root of 3, x plus y plus z. And then you got, 1 over the square root of 2, x minus y, and you got yourself a 1 over the square root of 6, yowzers, x plus y minus 2z. Of course, the opposite way around, x bar 1, x bar 2, x bar 3, since these are orthonormal vectors, this is a orthogonal matrix, right? So it should be equal to its inverse is equal to its transpose. Oh, that was also true for this one. Good grief. It's equal to its transpose, but this stupid thing's symmetric, so it is its own transpose. That was fine. That was what I was hung up on. Anyway, so the basis matrix here, is the so this we obtained from actually basis inverse times x, right? So conversely, x bar, y bar, so this is x bar, y bar, z bar, okay? So I keep flipping out of the 1, 2, 3 and x, y, z notation. My bad. So x, y, z is equal to just the basis matrix times, x bar, y bar, z bar. So the formulas are just fine. 1 over root 3, 1 over root 3, 1 over root 3. My second column is 1 over root 2, minus 1 over root 2, 0, and then 1 over root 6, 1 over root 6, 1 over root 6, oh, minus 2 over root 6. That times x bar, y bar, z bar. And so after some algebra, I am claiming that that works out to 3 x bar squared plus 2 y bar squared plus, of course, you knew it was coming, 42 z bar squared equals to 1. In other words, this equation here is in fact a tilted ellipsoid. It's a tilted ellipsoid. It's an ellipsoid which has been tilted off its axis. The axes of the tilted ellipsoid are namely this, this, and this. Those are the principal axes of symmetry of the tilted ellipsoid. Like if you can think of the egg being tilted, it works out to that. So if you actually work these formulas out, you plug them into that, and work through it, you get that. By the end of this course, you will understand how to do that without actually doing it, if that makes sense. Well, anyway, are there questions? I think I forgot. I thought it was like over time, but I'm actually under time. Wait a minute, what? That's impossible. Any questions about this? Let me take a breath. So let me repeat. If we have a orthonormal basis, we can calculate the coordinates by just taking dot products. So we don't actually have to invert the basis matrix in that case. See, because if we have orthonormal basis, we can take the dot product of our vector with the basis. See, like, how does x dot u2 look like? We've got x bar u1 dot u2 plus, I guess I should be putting, well, anyway, you understand. I'm sorry, guys. X bar 1 is equal to x bar 2 is equal to y bar, x bar 3 is equal to z bar. I do this, so my apologies. But x bar 2 here, u2 dot u2, plus x bar 3, u3 dot u2. So in this one, the fact that u2 is perpendicular to u1 and u3 kills off those two terms and just leaves you with the middle one. See? And this is 1. That's why I put this formula right here. That's how I can get y bar. I could not do this in my example 1 because the vectors 1, 2, and 2, 1, they're not orthonormal. They're not perpendicular, right? They're not normalized and they're not perpendicular. So we had to invert the matrix. We just had no choice in the matter there. Okay, well, I could do more, but I think I will stop. So.